I am Dr. A. Anita, Assistant Professor of Chemistry from V.V. Vanniya Perumal College for Women. In this module, we have entered into the gaseous state 4. In this, we will discuss about the Maxwell-Boltzmann distribution of molecular velocity and the different types of molecular velocity. In our previous module, we have seen the kinetic theory of gases and what are the different types of gas laws and how the kinetic theory of gases is proposed and what are the impacts of it and what are the drawbacks behind it and what are its limitations. In this module, we will see about the Maxwell-Boltzmann distribution of molecular velocities. Consider all the molecules are not moving with the same velocity. If all the gas molecules are moving with the same velocity, if a particular volume of a gas is allowed to move from one place to the other, then all the molecules will reach the destination at one particular time. But that is not the case. From time to time, each and every molecule reach the destination. That indicates that not all the molecules are having the same velocity. Different molecules have different velocities. Different molecules move with different velocity in their own path in order to reach their destination. This is the case. Therefore, Maxwell and Boltzmann, two famous scientists in the field of gaseous state, they have come out with the graph, that is the Maxwell-Boltzmann distribution curve. In this graph, the fraction of the molecules having a particular velocity is marked against the molecular velocity. This graph is drawn for two different temperatures, that is for 300 Kelvin and for the 600 Kelvin. Here the gas under study is nitrogen gas. That is, the total number of molecules is equal to the area of the curve under the study. If we take the total area, then we can get the total number of molecules. Then the total molecules are getting fractionated, are getting dissipated into small fractions and each of them having a particular range of velocity. Here consider the velocity is 0. As move on, the molecular velocity increases. Therefore, the molecules having the lower velocity are in a lower fraction. That is, only a less number of molecules are having a lower velocity. And coming to the other side of the graph, most of the molecules having the number of molecules having the higher velocity is also in a very low fraction. Whereas the number of molecules having medium velocity, that is not too low or too high or in a very high range, that is indicated by the bell-shaped curve. As when the temperature is raised from 300 to 600 Kelvin, the curve gets displaced from lower velocity to higher velocity. Here, the maximum of this curve gives the most probable velocity, and this is indicated by this equation. That is the total, it is a fraction, that is the small amount of molecules divided by the total number of molecules, that gives the fraction of the molecules having velocity between C and C plus dc. And the total number of molecules is N, whereas the small fraction is D and C, and M is the molecular mass and T is the temperature. It is an exponential curve, that is, it has no sharp beginning and no sharp ending. It goes on like this. That is, even at very low temperature or very high temperature, some of the molecules are having velocity and none of the molecules are having zero velocity. They move with some amount of particular velocity. This is the inference from the curve, and this is given here. Only a small fraction of molecules having very low or very high velocity. Most of the fraction of the molecules are having that average velocity, and the maximum of this curve is represented by the Maxwellian curve in the most probable velocity. That is, the most probable velocity is the velocity possessed by maximum number of molecules is given as the most probable velocity. When the temperature is raised from 300 to 600 Kelvin, most molecules having higher velocity increases. The number of molecules possessing high velocity increases, whereas only a very little amount of molecules are having a lower velocity. Therefore, the kinetics indicates that as temperature increases, the rate of the reaction also increases. This forms the basis for the rapid increase in kinetics when the temperature is raised. And next we come to the different kinds of velocity. The velocity of the molecules are classified into three types. That is, one is average velocity, The next is root mean square velocity and the most probable velocity. When coming to the average, it is nothing but a mean of the velocity. That is, velocity possessed by each and every molecule is getting added up and then divided by the number of molecules gives the mean of the velocity, that is represented as the average velocity. The average velocity is given by the equation root of 8 RT divided by pi m, where R is the universal gas constant, T is the temperature and m is the mass of the molecules. Next we get into the next velocity, that root mean square velocity. The average velocity does not hold good for all the type of equations. Therefore, the scientists at that time, they come into the next type of velocity called as the root mean square velocity. Here is also the mean is taken, but it is not the summation and then divided by the number of molecules. Here each and every velocity is squared and then summed up and then you are getting the root. But this also gives some amount of relationship when come to the application part, but this also has some disadvantages also. Here according to the kinetic gas equation, here mu squared will be equal to v1 squared. That is, we are taking the square of each and every velocity and then you have sum it up and find out the average. After that you are taking the root. That is, we are taking the square, then mean and then the root. That is why it is called as the root mean square velocity. Here three different functions are used, and when coming to the equation for this root mean square velocity, it is coming from the kinetic gas equation. From this kinetic gas equation, PV is equal to 1 by 3 mn u squared. We are taking the u squared and rearranging this equation, we are having like this, and instead of PV we are replacing it with the RT, as PV is equal to nRT according to the ideal gas equation. Therefore, the U is taken as 3RT divided by m, that is called as the root mean square velocity. Next type of velocity is the most probable velocity. It is the velocity possessed by the maximum number of molecules. It is only one velocity. We are not taking an average or the root or mean or anything like this. According to this calculation, Maxwell's calculation, the most probable velocity is given as root of 2RT divided by m. Next we will see about the relationship between these different types of velocity. All of the terms having, that is, the average velocity is 8RT divided by pi m root of, and u is equal to, that is the root mean square velocity, the same term by the pi, and we are having 3 instead of the 8. On having the relationship between this, that average velocity is equal to root mean square velocity into this factor, that is approximately 1, that is 0.92. When coming to the relationship between the root mean square velocity and the most probable velocity, most of the terms are same. Here RT is same, m is same, and here it is root 2 and here it is root 3. That is, the relationship between these two is the root 2 by root 3. That is nothing but the value is 0.8165. Therefore, most probable velocity is equal to 0.816 times of that of the RMS velocity, that is the root mean square velocity. And that's all about this relationship between these velocity. When one type of velocity is known, then we can move into the we can find out the other type of velocity also. If the most probable velocity is known, then we can calculate the root mean square velocity by dividing it with 0.8165. Once the root mean square velocity is found out, then we can find out the average velocity. Similarly, if any other velocity is known, then the other two types of velocities can also be calculated by simple numerical methods. And that's all about in this video. In the next video, we will see about how the ideal gases are different from that of the real gases are deviating from that of the ideal behavior, and how the real behavior exists in the world and what are the exemptions or how it is deviated from the ideal behavior by simple relationship. Thank you.